Okay, so for our last lesson, we're going to talk about chemical reactions. And I actually did this in a reverse order with the lab. We did a lab yesterday on chemical reactions where one of the things I wanted us to do is see a whole bunch of cool reactions, like when we lit stuff on fire, or when things change color. Now, I tried to find really cool, interesting ones. There were also a couple that maybe weren't quite so fast, like when I put the copper pennies into the solution, it was kind of slow. But I wanted to show you a good variety of chemical reactions, and that's our last concept here, is... You guys ready to learn, or do I need a few minutes here? I want your best attention, guys. If you're going to do your best, I need focus. You need focus. So, our goal today now is to really focus on chemical reactions now that we've seen a whole bunch of them yesterday. So I've got two things I need to talk about. One of the things we're going to do towards the end of the lesson is I'm going to talk to you about 4 types of chemical reactions that when you guys eventually write the PAT, you're supposed to know about. And so we'll cover those 4 at the end of the topic. Before we do that, though, I want to show you some of the characteristics of chemical reactions again, but more importantly, I want to show you how we write a chemical reaction on paper. Like, how does the writing of the chemicals look? So, quick review, though. What defines the difference between a physical change and a chemical change? And the biggest difference right here is that there's always something different or new when you have a chemical change. Maybe the word we should use is that a chemical change is not reversible. We've used that term before, right? You can undo a physical change. If you melt it, just freeze it. If you cut it in half, tape it back together. But if you undo a chemical change, like what we did yesterday, remember when I dropped that sodium in the water and it exploded? Try to undo that. Yeah, that's not going to happen, right? When I burnt that gummy jujube thing in the potassium chloride and it turned like bright pink, is that going to be something you can undo? Not really. But if I were to cut something in half or melt it, yeah, that you can undo. So today, the word we're going to use, though, for chemical changes, here's what we use instead. We call it a chemical reaction. This is the word. You guys have probably heard this word before. A chemical reaction is the word. And it's all about creating something new, or the word I'm going to underline here is something different. If you make something different or new that you can't reverse, that's a chemical change. Hopefully I'm being overly redundant here. Here's a slide that then re-summarizes some of the things we should have saw in our lab yesterday. Some of the characteristics of chemical reactions. Here's the first one. All reactions should have new substances. So that would mean that there's a new state at room temperature. Right? It used to be a solid, now it's a liquid. It used to be a liquid, now it's a gas. They might have a new color, they might have a new smell. Now those are the ones that we noticed. But there's more to that list. Like, for example, if there's a new melting point, or there's a new density, those would also count too. Yesterday in our lab, though, I just didn't bother to take the time to record density before and afterwards, or to record melting point before and afterwards. So in our lab, we mostly focused on state of matter, whether there was a smell, whether there was a color. But those are the main things we consider. So there's one. Second thing you need to consider. All reactions have what's known as a flow of energy. They either are going to get hot or cold.
Senator Big Bowl and Rihanna Antichuk, please come to the office.
We
Senator and Rihanna, please come to the office.
We noticed that many of our reactions give off heat. Not all of them were noticeable, but many of our reactions clearly burnt and lit on fire. Do you guys remember that one, though, where it actually got colder? So all reactions should involve some sort of temperature change. Whether it's enough that we notice it, like it might only change by 1 degree, but all of them should change. And then this one is kind of redundant because I already changed state at room temperature, but you may notice gases or solids appearing. Sometimes there's a phase change. This really shouldn't have been new information because we've already talked about these things in our labs and in our notes. Kids in the hallway are just keep going. Anyways, hopefully I'm making sense here in that these are all reaction characteristics that we looked at in our lab. Sarah, can you grab that door there for whoever? So I need to introduce some new terminology now, though. And maybe you've heard these words before. I'm going to use my highlighter here. The words I need you to be aware of are the stuff that we start with, we call them reactants. whatever we begin with, the chemistry word for that is reactants. So when I began with a water and sodium, that's a reactant. The things that we make, the word we give to those is we call them products. So before is a reactant, afterwards is a product. And that's just the word we use. Now, one of the ways in which on paper, this is one of the two goals I have for you today. One of our goals is to know on paper, how do we look at chemistry notation and recognize a chemical reaction? This would be a great example of one. So let me just start doing some highlighting. Where's my pen? Here it is. This would be a good example of how we would write a chemical reaction on paper. And it looks something like this. I would take my first compound that I used, NaCl, sodium chloride, and water. And these two things over here, this would be what we started with. Which is why we write them kind of like from left to right, just like when you read. Whereas these two things over here are what we finished with. And in the middle, we always draw an arrow. Now, like in math, when you write an equation, what goes in a math equation kind of in the middle? Yeah, an equal sign. In chemistry, rather than using an equal sign, they'll use an arrow. Okay. And so this really isn't that much different than it being like, say, 3x plus 4 equals 7 plus 2x. If you guys do math like this is what you're starting with, this is what you're finishing with, and there's a sign between it. It's kind of the same concept. Only I need you to know the words. These are called reactants because they are what react. And these are called products because that's what we produce. Does that make logical sense? So I just need you guys to know the vocabulary today. But I also want you to be able to look at a chemical equation and be able to figure out, like, well, what happened here? And this is where, in the last couple of days, I taught you guys how to name substances. This thing right here is sodium chloride. This thing right here is water. So now you might know, okay, take sodium chloride and add water. And what does it make? Well, it makes sodium hydroxide and hydrogen chloride. And hopefully you can kind of identify what is happening. Now, one of the most important things we have to do when we're writing chemical equations is follow Antoine Lavoisier's law of conservation of mass. Okay. We talked about him many lessons ago. I think it was like the third or fourth lesson. We talked about Lavoisier. He had an experiment he did where he realized that if you ever start with a certain amount of mass, like say 10 grams.
Come back to the office. Strider, please come back to the office.
If you do a chemical reaction, he realized that it always ended with the same amount. However much mass you start with, you always end with that same amount. Hence the name law of conservation of mass. But we need to make sure that we show that when we write our chemical equations. And I'd like to show you how we do that on paper on my next slides here. Okay. Here's another picture though, kind of illustrating what he did. He took some magnesium, 24.3 grams of it. He took some sulfur, 32.1 grams of it. He took these two things as reactants, and he combined them together to make a product. And what he discovered is magnesium sulfide, it ended up actually weighing whatever this one plus this one was. It equaled the final one. We're actually going to do this on Friday. On Friday, what we're going to do is we're going to weigh chemical A. We're going to weigh chemical B. We're then going to react them together. And then we're going to weigh how much they collectively are when we're done. And ideally, A plus B should always equal A plus B. Like whatever we start with, it should equal the masses afterwards. Right. That's a great question. That's actually what I got on this picture right here. When ancient chemists were trying to do this, they might have actually discovered that 10 grams they started with, they might have done some math and realized that it actually equaled, say, 7 grams. And they'd be like, well, where did the other mass go? Well, the reason why is that when you burn stuff, often it gives off gas. Yeah. And so there might have been, say, 3 grams of gas being released. And so it kind of looks like you start with 10 and finish with 7. But when you burn it, that's where the missing mass ends up going. Does that answer your question, Courtney? Okay, what I'd like to do is show you kind of in a picture format then what a chemical reaction might look like. I want you to count these ones up here. When we started, there were 1, 2, 3, 4, 5, 6 individual white particles. Everybody's clear with that? And when we started, there were 1, 2, 3, 4, 5, 6 individual big blue particles, or purple, whatever color you see. Now, according to Lavoisier's conservation of mass, if I start with 6 of, like, say, these ones, and I start with 6 of these ones, I should have the exact same number when I'm done. But you'll notice these compounds are different. It used to be that the whites were together and the blue were single, but now in this one right here, white and blue have now combined somehow. So a chemical reaction has taken place, but the point is that there is still 1, 2, 3, 4, 5, 6 of each of them. It would not be fair to have like this one not be here. You can't start with 6 and finish with 5. Does that make sense? That's what Lavoisier determined. And because of that, when we write a chemical reaction, we have to write it according to balanced conditions. And that's what I want to show you as the first main part of my lesson. On paper, when we try to write an equation, there are a couple of things that we do to balance an equation. Okay. Now, one of the things I've already showed you is these little numbers right here. If you guys recall, those little numbers right there tell you how many you have. Oxygen right here comes in a package of 2. So there's 2 oxygens right here. And right here, this hydrogen right here also comes in a package of 2. So if I were to draw this out, you really have 2 hydrogens. And I want to use an open circle here. You have 2 oxygens right here. That's what we started with, 2 of each. Now, what I produced is water. Water is H2O, which means you need 2 hydrogens and 1. We don't write the 1 there, but there's 1 oxygen needed. Here's the problem, though. We have broken the law of conservation of mass because there were 2 of these to start. Okay, there are 2 of them to finish. See how there's 2 of these guys right here, but there's only 1 to finish. According to this, we actually have a huge issue because mass was not conserved. So when we write a chemical equation, here's what we would actually do. We would write it like this. H2 plus O2 goes to H2O. But we put a big coefficient in front, like this. We'd say, what if I had 2 hydrogens? See how there's 2 hydrogen 2-packs. And I had 1 oxygen 2-pack. And when I was done, it made 2 waters. And what we do is we change the recipe. I like to compare this to cooking a lot. Sometimes the recipe in cooking requires 2 eggs to a cup of sugar to half a cup of flour. It's not always like 1 of everything. Sometimes you need 2 of these and 1 of these in your recipe. Now look at what happened when I actually changed the amount I had. Now there's actually 1, 2, 3, 4 hydrogens. And afterwards there's 1, 2, 3, 4 hydrogens. That's good. But now count the oxygens. There's 1, 2 oxygens. And over here there's 1, 2 oxygens. Long story short, when we write chemical equations, you're going to see some numbers in 2 different locations. One of the locations will be the small little subscripts right here. And that tells you how many of each thing is inside a molecule. So when you see H2O, it means that there are 2 hydrogens for every 1 oxygen inside that molecule. But when you see this big number 2 in front, that tells you how many molecules you need in your recipe. And so I want to show you that in the next couple of slides in terms of how a chemical reaction looks. Here's that same reaction now written properly. If you see a 2 in front, it means you need 2 hydrogens. But the hydrogens come in a 2-pack. So here's a 2-pack of hydrogen. Here's a 2-pack of hydrogen. I need 1 oxygen. So there's just the 1, but see how oxygen comes in after the 2-pack again? And when you're done, you're going to make 2 waters. So here's 1, 2 waters. How is water made? Well, the water has 2 hydrogens and 1 oxygen. So 2 hydrogens, 1 oxygen. This is how we write ourselves a chemical reaction. However, anytime there's a number 1, just like in math, we don't usually write the number 1. So when there's just one oxygen right here, we kind of skip right in. And when you have to use one molecule of oxygen, we don't bother writing that one either. In Science 9, you guys aren't expected to write chemical equations. Okay? So if you're looking at this going, whoa, where did this come from? That's fine. But you're expected to be able to look at a chemical equation and interpret what is happening. That's it. That's the expectation. So if I show you a reaction on paper, like say this one right here, you should be able to look at it and understand what is what. Like this arrow right here separates the reactants from the products. You'd be able to recognize, okay, we started with carbon as a solid and oxygen as a gas, and we made carbon dioxide. Okay, that's the expectation. One of the most common questions they ask in a PAT might be how many atoms were being used. And this one right here is really basic. The answer would be 1 carbon reacted with 2 oxygens. Whereas if I were to go find, we're going to find another example here further on our notes. Here's a really complicated one. You guys can see this one right here. Right here, I might be asking you, how many oxygens were used? And then this becomes a little challenging because you'd have to know what this right here means. If I asked you how many oxygens were being used, the answer would be 38. And the reason why is that you have 19 packages of 2. 19 times 2 is 38. Does that make sense? Or right here, in this example right here, if I asked you how many carbons are there? In a molecule, one molecule, there's 6 carbons. But we don't have one molecule, we have 2 molecules. So if I were to ask you how many carbons you'd have, you'd say that carbon there are 12 of. If that made sense to you, how many hydrogens are in this grouping right here? Well, there's 14 if you have one of them, but we don't have one, we have 2, so 14 times 2 is actually 28. This is a really common PAT question. They would give you a chemical equation, and they would then say, how many of each atom is there? And you'd say there are 12 carbons, because 6 times 2 is 12. You'd say there are 28 hydrogens, because 14 times 2 is 28. And you'd say that there's 38 oxygens, because 19 times 2 is 38. That's the expectation. As long as you can read a chemical equation, kind of know what's happening, we're good. So let me go back to the slides I skipped here. Let's look over one more example here, then we'll move on to a new kind of topic here. If I were to give you this equation right here, do you understand what's happening? How many carbons do we need in the total reaction? And the answer is 1. Some kids might say 2. They'd say there's 1 right here and there's 1 right here. They'd say here's a carbon, here's a carbon. They'd say there's 2 carbons. Why is that incorrect though? Yeah, we started with 1 carbon right here, and then we finished with 1 carbon. So there's not 2. We started with 1, and we ended with 1. If I were to ask you about hydrogen, you would say, well, there's 1, 2, 3, 4 hydrogens when I started. And when I was finished, there were 1, 2, 3, 4. And I can tell that by saying, well, look, there's H4 right here. If I were to ask you about the oxygens, you'd say, well, there's 4, because right here, 2 times 2 gives 4. There's a 2-pack right here, a 2-pack right here, that's 4. And look, here there's 1, 2, 3, 4. They got separated and used everywhere, but does that make sense to you guys? Everyone's paying attention at least. Those of you who are on phones that don't notice, you should pay attention, guys. Oh wait, another thing we need to talk about here. All chemical reactions I mentioned either need energy or they give off energy. They either get hot or cold. We actually have words for that. And you guys need to know this vocabulary. The words are exothermic and endothermic. They're on these next 2 slides. Here's exothermic, and here's a slide on endothermic. Let me start with exo. Exothermic reactions are reactions which give off energy. A lot of people, they remember this because exo starts with X, and it's like exit. Energy is exiting the system. When we light something on fire, we call it an exothermic reaction because it's giving off heat. that make sense? And many of the reactions I showed you yesterday were exothermic because they lit on fire, they produced energy. Now energy can be heat, but it can also be light or sound or something like that. So if it gives off a sound, it was actually exothermic. Even if it doesn't give off heat, it can still be exothermic. The opposite of an exothermic reaction is an endothermic reaction. And these are reactions that absorb energy. Now, reactions that absorb energy usually are cold. Brief side note, there is no such thing as cold. Cold doesn't exist. Cold just means you lack heat. I want to say this again. Cold doesn't really exist. Cold just means that it's not hot. There's no such thing as darkness, by the way. Darkness just means that there isn't a lot of light. Yeah. Some people say the opposite of hot is cold, but like from a chemistry perspective, if you feel that something's cold, what you're really feeling is your body is giving away its heat and heating up the cold item. Heat always goes from hot things to cold things. So if you're feeling cold, the reason why you're feeling cold is because your body is giving away its heat to the surroundings, and that's why you start to shiver and you feel cold. But cold doesn't really exist. You're just losing heat. Does that make sense? I often say to kids, actually, I do it in groups of 3. There's no such thing as cold. There's just a lack of heat. There's no such thing as darkness. There's just a lack of light. The third one. There's no such thing as stupid. There's just a lack of knowledge. It just means you haven't learned it yet, that's all. So never call yourself stupid. It just means you haven't learned it yet. Alright, anyways. A cold pack is a great example of an endothermic reaction because it needs energy to run. It feels cold because it's absorbing your energy.
Girls, really.
If you want to go, just go. I'm dead serious, guys. If anybody else just does not want to learn right now, you're wasting my time. You're wasting your time. Give me your best effort. If you give me your honest to goodness best effort, I will do everything I can to help you learn. But I can't do that unless I get your best effort. Yesterday we had one reaction, which was endothermic. If you guys recall this one, it felt really cold in the bottom of the flask. What was really happening is when you guys put your hands on the bottom of the flask, the energy from your hand, you know, we are kind of warm, the energy from our hands was going into the flask and heating it up. And it was actually making us feel cold, but it was soaking and sucking the heat out of your hand when you were feeling it there. So we don't actually really feel cold. What we really feel is our body losing heat. Does that make sense? When you crack one of these cold packs right here, I know we call it a cold pack, and that's fine, but it's really, what's happening is it's an endothermic reaction, and it feels cold because it sucks in heat. All the heat from the surroundings gets sucked into it. Whereas, when you have an exothermic reaction, heat emanates and radiates out of it. Can you guys see the difference in these pictures right here? When something is hot, the reason why it's hot is because heat, or energy of some kind, leaves it. And we feel that heat radiating around it. Say there's a fire, and you stand near the fire. This fire, the heat goes out towards you and you feel warm. But when you have a cold pack, what's really happening is you, as a person, are losing your heat to the cold pack, and that's actually why you feel cold. Is that clear to everybody? So, mini science lesson here. There's no such thing as cold. Cold is really just when you lose heat. Long story short, I need you guys to know about endothermic reactions and exo. Most kids, they remember exo because exo means exit. And that helps them get it started. Very loud out there. So that's actually what I have written on this slide right here. So exothermic means that energy exits. Endothermic, some people use this, they say endo means energy enters, and it absorbs energy. Okay, last topic. For your PAT, you guys are expected to know about 4 kinds of reactions. Okay? If I can give you guys some advice, write these down on your formula sheet. You know your periodic table? Write these ones down. It would not hurt to have them nearby. Now, just so we're clear, these are not the only 4 kinds of chemical reactions that exist in the entire world. But these are just 4 common ones that they want you to know about. So here's the 4. Combustion, corrosion, photosynthesis, and cellular respiration. So I'd like to walk you through the basics of these 4. And then actually that's it. Then I've covered the entire chemistry curriculum. So I have a slide on each, so you probably don't need this slide to write them down from. I'll go to the first one here. The first slide is combustion. And a couple of the reactions that we saw yesterday were combustion. Combustion is basically whenever you blow something up using oxygen gas. Let me say that again. Combustion is more or less whenever you blow something up using oxygen gas. And I'm going to highlight that right here. In order for it to be combustion, it must involve oxygen reacting. And it basically explodes, it blows up, it gives off a huge amount of energy. For example, when I put that piece of sodium inside the water beaker, and it then went boom, that was combustion. Okay. The reason why is that it rapidly ignited with oxygen. You guys ever seen a little triangle like this? In order to start a fire, you need 3 things. You need a fuel. In that example is a little piece of sodium. You need heat, which gets given off by it lighting on fire. The last thing you need is air, because the air is what gives you the oxygen. You guys know, like a fire extinguisher? You know how a fire extinguisher really works? It suppresses the oxygen in the fire. It removes the oxygen. It's like a fire blanket. What you're trying to do is remove one of these 3 pieces. And if you can get rid of the oxygen, well, then it doesn't stay on fire anymore. Now, we use combustion in so many things. Let me give you some examples. We use combustion to heat our homes. We burn natural gas in like methane, and we use that to create the heat, but then we then pump through our ducts to then help us heat our houses and our schools and stuff. If you were to cook food on a barbecue uses propane, we are combusting it. Does that make sense? A lighter, just like a basic cigarette lighter, we're using butane. It is also combustion. So many things that light on fire are usually combustion. So what I need you guys to know, the 2 biggest things about these, is that you always need to have oxygen. And it always makes energy. It always gives off heat and light and like fire, basically. But they all need oxygen to occur. Now, this example I have right here is actually gasoline in your car. Hexane would be this compound right here. But this one here can change. It does not have to be hexane. It could be propane. It could be methane. It could be so many different chemicals will combust. It could be hydrogen even. So what I need you guys to know about combustion, it always starts with a substance, a fuel. You can change the fuel out to something else. But it always involves oxygen gas. There's one more thing about it, though. These days, climate change is a major issue, and one of the reasons why climate change is an issue is because of this product, carbon dioxide. Almost everything that combusts gives off carbon dioxide, and it contributes to global warming and greenhouse gas emissions, which is why, maybe you guys have heard of things like a carbon tax. Okay. Anything that combusts, especially in Alberta nowadays, is subject to a carbon tax, which is all because of this carbon dioxide. That's combustion. It would be exothermic. It gives off energy. Sound good? Next one you need to know about. This one's called corrosion. And you guys probably have some familiarity with corrosion as well. We give this another name sometimes. We call it rusting. Now, rusting is usually the name we give when iron corrodes, but lots of metals can corrode. I showed you guys some samples of copper and magnesium in the lab over a while, and sometimes there was like some tarnished areas on the outside where like if I scraped it off, it became nice and shiny underneath. Okay, that's corrosion. Now it doesn't have to be rust, but rust is if iron corrodes. But it could be magnesium, it could be sodium, it could be anything. Okay? So like this thing right here, again, this can change. You can change what you corrode. It could be copper, it could be zinc, it could be magnesium, it could be anything. But the basic premise is still the same. Corrosion happens when you add it, again, to Oxygen, actually. Many metals just corrode when they're just left out in the air. So as soon as we add this oxygen right here, it causes metals to corrode. The biggest one that's a problem is iron. When iron corrodes, it starts to look kind of like this. You guys have seen like rusting before, I'm sure, right? But here's the reason why rusting is a problem. It flakes and it breaks. Iron is normally really strong, but as soon as it starts to rust and corrode, you can flake and chip it off. Anybody seen like a rusty old car? Like it starts to like disintegrate almost, which is why iron has huge problems with this. Other chemicals, by the way, they corrode, but they don't disintegrate. Aluminum, for example. Aluminum, when it corrodes, it puts a light clear film around the outside, and the aluminum itself is actually still really strong. So many things get made out of aluminum because they don't get weaker when they rust. Often we try to make things out of stainless steel. Ever heard of that before? Because then it shouldn't rust at all. And we try to then prevent the whole problem of what happens when these things start to break down. Because eventually these chains right here, they'll become brittle and they'll break, right, as they rust more and more. So that's corrosion. Second one you should know about. It does not have to be iron, but it definitely involves oxygen. My third one you should know about. It's called photosynthesis. And maybe you've heard this at some point before in like, I think Science 8. I think we talked about this. This is what plants do. Plants take sunlight and they make sugar out of it. Yeah. The basic concept is you have to have light. A plant has to have sunlight hit it. But it also takes carbon dioxide, and most important thing here, you have to water a plant. If you don't water a plant, it will die. Okay? But if a plant has all three of these ingredients, carbon dioxide from the air, water from you watering it probably, and light, it can then produce a sugar. And then that's how the plant actually lives. Now, one of the really cool things about plants is that they actually help us against global warming. Carbon dioxide is a pollutant that causes greenhouse gas emissions, but the cool thing is that plants use carbon dioxide and they turn it into oxygen. So plants actually clean our air for us. There are some places in the world, the Amazon rainforest, where because there is so much trees and vegetation there, that there is a huge abundance of oxygen in the atmosphere. There's actually more oxygen there than in other places because all of the carbon dioxide gets filtered back into oxygen. Here's the thing I need you guys to know about this one right here. This right here is an endothermic reaction. Now, it's not cold in the same way that it absorbs heat, but it does require light. And so since it has to absorb in something, that's endothermic. Let me go back to my photos from the previous slide. Here was my picture of something hot. If energy is being given off, it's exothermic. But if energy gets absorbed in, it's endothermic. Often it's heat that gets absorbed in, but it could be, like in this picture right here, light getting absorbed. So this one is unique because it's the only endothermic reaction you need to know about. The rest are all exothermic. Wait, here's the last one. This one is known as cellular respiration. And it's what we as humans do when we eat food. When we eat food, food is often in the form of, like, say, proteins and carbohydrates and stuff like that. But long story short, eventually your body will break them down into sugars. Through the digestion process, your body will have sugars in it. Some unhealthy ones, some healthy ones. Your body will then take that sugar, and because we breathe in oxygen gas, what it does is it gives us the energy we need to go do stuff. So when we eat food and our body turns it into sugar, it's food, and we breathe in oxygen gas, it gives us energy. But there's two other byproducts, by the way. When we breathe in, we're actually using the oxygen. But when we breathe back out, we're actually breathing out carbon dioxide. So we're actually contributing to carbon dioxide problems just by our breathing, actually. We breathe in the oxygen, we use it, and then we breathe back out carbon dioxide. There's actually one more byproduct, though, too. There's actually water involved, H2O. Water actually makes a lot of sense for two reasons. One, when we consume different foods and drinks and stuff like that, we actually have to expel excess water when we go to the bathroom. Okay? But two, our body is made like 70-something% of water. Like our body is a large part water as well. This is one of the reasons why. So this one right here, the basic things you need to know is that it also requires oxygen. Many of these examples we did here all need oxygen. Let me look back to the moment. This one right here needed oxygen to start on fire. This one right here needed oxygen to rust. Here's the cool thing. Plants give off oxygen. But humans, again, need oxygen. So many of these reactions are all oxygen dependent. So, long story short, I had two main goals for the day. Two things I need you to know about. One is I need you guys to know the 4 main reactions. Okay. There are more than these 4, but those are the 4 that are on your PAT. The other thing is I need you to go and look at a chemical equation, and you should know what's happening here. If I were to ask you what are these guys here called, you should be able to tell me that it is a reactant. If I asked you what these guys right here were called, you should be able to tell me that those are products. If I tell you that it releases energy, you should be able to tell me that it is exoenergy. And if I were to ask you in this molecule right here, how many oxygens are there? You would say 12, because in a package of 2, you have 6. 6 times 2 is 12. Okay. So those are some of my goals for the day. I have one last slide, then we're actually done chemistry. Here's the last slide. Yesterday when we did our lab, you might have noticed that some reactions were very slow. But there were a couple of them. Some of them were actually quite fast. Like, for example, when that sodium blew up in water, it probably surprised a few of you. It surprised me. Like, it was boom. But there are some reactions, like, say, rusting. Guys, focus, please. I'm almost done. Which are exceptionally slow. We have a name for that. We call that a reaction rate or a rate of reaction. And I've got actually the 4 we talked about here. Cellular respiration and combustion, those happen quite quickly. When we breathe in, that happens fairly quickly. And when we blow things up, it happens pretty quickly. But plants take a really long time to grow. Right? Like a plant takes years for it to go from a little seedling to a big large plant, big large tree, right? And same thing with corrosion. Rusting takes years to take place. So I need you guys to know the term rate of reaction. Basically, how fast does it occur? There are 4 things. Stay with me, guys. We're almost done. 4 things that affect the rate of reaction. And basically, I would write these down while we're writing these down. Here are the 4. The concentration of reactants. Did you guys know what that means, though? Concentration of reactants means if you use more, it'll happen faster. No, yesterday when I put that sodium in the water, a couple of you were like, put the whole thing in. I would not, because I saw how much the little piece blew up. But in theory, if I used more, it would happen faster and larger and bigger, right? So that's what concentration of reactants means, is how much you use. You probably can't see that, can you? Concentration is how much you use. Okay. Second thing, temperature. We actually notice this when it comes to things like a freezer. Why do we put food in a freezer? Well, the reason why is that it prevents the molding process. All food will mold and rot over time, but by decreasing the temperature, it slows down that reaction rate. Okay? Now, food doesn't last in a freezer for 50 years, necessarily. Usually gets freezer burnt over time. But by dropping the temperature and lowering the temperature, the reaction actually slows down, and bread doesn't mold, and meat doesn't rot with maggots and gross, whatever, right? So temperature also helps. Third one, surface area. We actually notice this when we eat our food. Humans have teeth, so we can chop our food up into small bits. And the reason why is that when we chop it into small little pieces, our bodies digest it easier. When there's more surface area by making it smaller little pieces, it reacts better. Okay? If I were to take 2 things right here, if I were to take a clump of something and try to dissolve it in water, or if I were to try to break up little pieces like this, the smaller pieces always dissolve better. So if you have more surface area, it also works better. And then the final one here is a catalyst. If you don't know what a catalyst is, it basically is a device that speeds up a chemical reaction. That's literally what we define it as. A catalyst is something that makes a reaction go faster. Now, you'll learn more about catalysts as you take biology, because there are a lot of catalysts involved in biological processes. But for right now in Science 9, that's literally where we stop. We basically just say, look, a catalyst is an item that makes a reaction happen faster. So those are the 4 things. Heat it up, it goes faster. Use more, it goes faster. Grind it up into pieces so there's more surface area, it goes faster. Or use a catalyst, it goes faster. Some things happen quickly, some things happen slowly. Okay, that's it. That's all I got, guys. Does anybody have any questions? Thanks. Really good thoughts. Okay.